Well, good morning, everyone. I'm Dan Dumbacher, former CEO of AIAA, but now professor of engineering practice at Purdue University, out in the middle of the cornfields and the soybean fields. We don't know how to play football there. We do know how to play basketball. I will leave it at that. And today, what we want to do is celebrate and begin the celebration of Robert Goddard's, the 100th anniversary of Robert Goddard's first flight. And you see the picture up behind me, very famous picture, everybody has seen this, but we want to recognize and talk about where we have come over the last 100 years and where we are going the next 100 years. So this is a little bit of a look back and then a look forward, and to help us do that today, we have Kristen Houston here from L3 Harris / Rocketry. I am sorry, Kristen. I'm a longtime shuttle main engine guy, and I can't get the word Rocketry. I still have to use it.
You're not alone, okay.
Okay. And then we have Dr. Dan Irwin from the Viterbi School of Engineering at the University of Southern California, along with Dr. Troy Henderson, Professor of Aerospace Engineering at Embry-Riddle in Daytona Beach. Correct?
Yeah.
I always mess up Florida with Arizona. And what we want to do today is talk about where we have come, as I mentioned, in the last 100 years, since Robert Goddard had his first flight test back on March 16th of 1926. We went a whole 41 feet and landed 184 feet downrange. Now, those numbers don't sound big today, but they were extremely important at the time. And now today, we go from 0 to 17,500 miles an hour in the space of 8 or 9 minutes. Even Peggy this morning in the plenary referenced that. The important discussion here is the beginning steps to get us from the surface of the Earth to orbit and orbital velocity. There has been tremendous progress over this 100 years, and we're going to talk about that. And it's not just progress to orbit, to Earth orbit, it's progress from Earth to the moon and beyond. And you'll hear about all of that. We're going to discuss the next major rocket propulsion and space transportation accomplishments that we think are ahead. And with this extraordinary panel and the expertise and the knowledge here, we have a lot to talk about in this hour. And I think hopefully it will be a thoughtful, provoking, and a very educational session for everyone, because this is the topic that helps us start everything we try to do on orbit and in space. So with that, enough for me. Let's talk about the past 100 years. And I'm to all of the panelists, what do you see as the accomplishments, the lessons learned in rocket propulsion over the last 100 years? What and how have those accomplishments allowed humanity to extend its presence in space? So for kicking all this off, Kristen, I'll go to you and L3 Harris / Rocketry.
Thanks, Dan, and welcome everyone. Thanks for coming this morning. What we're showing on the screen here, so I do come from the rocket company, you can just see the history that we have, over 60 years of launch and getting to orbit over many storied rockets, including today, of course, the Atlas V, the SLS rocket, and Vulcan, where we provide propulsion. But it's not just about, Dan, like you said, it's not just about launching and getting off the ground. That's important. We make boost engines, we do upper stage engines, but then also what we do when we get into space. And when I think about the milestone of 100 years from Goddard's flight, it was only 35 years till we had the first human space flight after that. So a really huge accomplishments in a pretty short period of time. And then we've been flying, our RL-10's been flying for over 60 years, I think from 58, I think was the first launch of that, right? So a lot that has happened and a lot still to come. So things I think about are really about the reliability of engines, really liquid and solid rocket motors and solid rocket boosters that have enabled the access to space and all that we've learned and have taken over those 100 years, and the technology and things that have developed that we wouldn't have had otherwise. So really thinking then also about the reliability and then the efficiency of these engines. So, okay, we talk a lot about the RS-25, but I actually want to talk about, reusability, and that, the SSMEs were reused many times and are going to be reused some again on the upcoming Artemis launch. But I also want to highlight a little bit about the RL-10 upper stage. Again, 60 plus years of flight and going back from Saturn I and today flying on Atlas, Vulcan, and SLS. But that has been evolved over many years and is very precise and efficient locating to get mass to orbit and exactly where we need to be. That's been done with a lot of involvement in additive manufacturing, where we're driving costs down. We have a new completely additively built thrust chamber assembly on the new RL-10E1. So a lot of evolution. The RL-10 of today is not the same RL-10 of 60 years ago, but it was the first ever liquid oxygen, liquid hydrogen engine ever in the world. And then we can see what that technology has continued to build with the stage combustion and cryogenic propellants, allowing us to be able to put a lot of mass into a precise location in space. And then the RL-10 also, going back in the history, it's really part of the foundation of today's reusable rockets that we see at SpaceX and Blue Origin. Back in the 90s with the Delta Clipper demonstration, our RL-10s, because of the ability to relight and be reused over and over, were really foundational to that program. And that innovation and that technology development really then is the genesis for what we're seeing in the reusable rockets today. But again, like I said, it's not just about launch. I think also the precision about on-orbit maneuverability is really important. So at L3Harris, we make not just boost engines like the RS-25 and the upper stage like RL-10, but a lot of the in-space propulsion, our thrusters that are on, from satellites to deep space probes. But what that allows, and then importance, I think we're going to see more and more importance of that need for maneuverability, whether it's from a national security space perspective. We hear about maneuvering without regret or space dynamic operations, and what we're going to need against some of our adversaries for more dynamic movement in space, and that's all going to require the propulsion elements, some of the smaller propulsion elements, to again that precise ability to control spacecraft, whether it's the Parker Solar Probe going closest to the sun we've ever sent anything, to Voyager, which is still flying in interstellar space today. So a lot of that I think is going to continue to go. So I think about, in summary really, it's about the precision, the reliability, and the efficiency that comes from rockets over the past 100 years.
Excellent, excellent. Thank you so much, Kristen. Troy, your thoughts on what you've seen over the last 100 years and the major accomplishments and what it's a...
You and me or
Dan? I meant Dan. I'm sorry. See, I'm not awake yet. All right. Sorry.
Still Monday, okay.
I think historically, if we take 100 years ago as being basically 0 and getting to the moon as 100, actually like 70 or something was achieved by the V2 program. And what's quite amazing about that is that I'm not pro-Nazi at all. Just from a technical point of view, don't post anything about saying I'm pro-Nazi in any other way. But the V2 had everything that we now recognize as being a fully functioning liquid rocket program. I mean, if you somebody who worked on the V2 program, if they went to SpaceX today, they would recognize almost everything they see. Not, of course, an additively manufactured intake manifold or maybe gimbal thrusters or gimbal thrust vector control, but everything else, turbopumps, cryogens, film cooling, regen cooling, they pretty much had it all, and they had it at scale. Do you know something? 5,000 or 6,000 of those things were manufactured during wartime conditions, which is pretty insane if you think of the conditions of wartime Germany. So to go from V2 technology to the moon is not actually as huge a step, I don't think, as going from nothing to V2. Now, I'll tell you one thing that worries me, though, historically, is that time and again, people worked on, bright young chemists had ideas for new propellant combinations, and they would test them, and in the worst case, there would be a wrecked lab and injuries and maybe even deaths. And the result of this in the pre-internet age was very often just a paper that went in a file cabinet. And I'm worried that many of these papers and file cabinets are being thrown away now, and we're going to be doomed to repeat these mistakes. So I'm coming from this, I don't have a long history with liquid rockets at all. In fact, it was just the opposite. I was a physicist and electrical engineer, and I kind of backed into all this because I was teaching a course in laser diagnostics, and a guy from JPL, the Electric Propulsion Lab, was in the audience, and he asked me afterwards, could you do this stuff in the plume of an arc jet? And I said, what's an arc jet? So we actually got some research going, and actually it was because of that meeting, I think, that I got tenure. Otherwise, I would have done something completely different. So funny how the world works. So I did some time in electric propulsion, and then I have this student group at University of Southern California. They do solid rocket. They build and launch solid rockets with the goal of being the first student team to space, which they actually achieved in 2019. So we'll see what happens with them in the future. So I think I'm done.
Great. Troy?
Thanks. So, Kristen and Dan, both, you hit on what I was going to talk about, the downside of going last. The fundamental physics of rocketry has been known and written down for 400 more years, right? So it's the technology development which has happened in recent years, thanks to people like L3 and others, but I have to say Rocketdyne, right, Dan? So it's the implementation of all of these concepts. Kristen, you hit a big one, the being able to relight, being able to throttle, like you said. Some of that has only come about in the last few years, right? I mean, it's a handful of decades between the Wright brothers' flight and the Goddard flight, but then another couple of decades between that flight and landing on the moon, and then another couple of decades between then and now. So it's, we're talking about one person's lifetime here in terms of time, which is kind of unreal to think about the exponential increase in what we can do in terms of the technology, but what that's allowing us to understand in terms of space science, technology development, how that benefits things not just on rocketry or on spacecraft, but for all, even here on Earth.
Excellent, excellent. Well, I want to add one, a little bit of moderator's prerogative here, and I thought I saw my good friend Joaquin Castro walk in here. I did. He's guilty as charged. Where we actually use the RL-10 for liftoff on a certain program called DCX and DCXA. And what that enabled, the work that you guys did, Joaquin's team did, actually facilitated the beginning of this renaissance that's being led by reusable landing of rocket systems. And that kind of facilitization, helping make things happen, that's just a shining example, I think. And then that workforce that did the X and XA programs actually went to SpaceX, Blue Origin, and moved on to go take it to the next level that we see today. So all extremely important. There's been a tremendous amount of progress over the past 100 years. And I think we see it manifested every day. I'm going to go to, just for awareness, I'm going to go to audience questions after the next section. So feel free to put your questions into the question tool, and we'll be happy to take your input and work with that. But let's start looking at the next 50 to 100 years. What are some of the major accomplishments or hurdles that we need to overcome over the next several years to help facilitate this new emerging space industry and everything that's out there? Is it getting the cost to orbit down? How do we do the maneuver without regret and the dynamic operations? What are those major accomplishments that we need to get in place over the next 10, 50, 100 years to be able to do what we as humans want to do in moving further out from Earth? Kristen,
Okay. Well, I'm going to just go nuclear right off the bat here, first thing Monday morning. But I really believe that we need to continue working on nuclear, both propulsion and power, but all things nuclear, and that is going to unlock a lot of additional opportunity for us in space. So when you think about nuclear thermal propulsion or nuclear electric propulsion, we're really on the verge of that, of creating that technology again. Well, I should say again, because actually 60 years ago, the Heritage L3 Harris companies actually launched the only U.S. nuclear reactor into space, the SNAP-10A. So it was 60 years ago, actually, last year was, so I guess we're coming up on 61 years from that. And we actually did that in 5 years from start to launch. So we know that's doable today. We're seeing a lot of great support out of the new administrator, recognizing the need for this technology, because this is going to dramatically shorten times to places like Mars. So if we think about a nuclear propulsion system, could take astronauts to Mars in 3 to 4 months versus a 6 to 9 month period, reducing the exposure to radiation. A nuclear electric propulsion system would be much more efficient on staging cargo out and further out. Continuing the exploration in deeper space. Again, more efficient, longer time for fuel. So I think continuing development on power conversion, power management and distribution. There's a lot of great work being done in terms of on the reactor side as well, but continued development there. I think we just need to have that consistency of leadership. It's kind of been in and out over the past many years. So I think we're seeing that now, but seeing the continued funding. But I think that's going to really be a game changer on what we can do, the access to space, the speed we can get there. And then from a nuclear power perspective, I mean, I always think about how many devices do you power every day, constantly, right? I mean, I'm plugging in a lot of things throughout the day. When we get to the moon or to Mars, everything's going to need power. Rovers, the ability to create, generate fuel, air, life-sustainable habitats. And so fission power, there's been a lot of work on that. We're continuing to work on that. The Artemis program has that baselined into its architecture for fission surface power. We're seeing some work done there. And so I think that, again, is going to be needed. So really all things nuclear. And then even with a nuclear electric propulsion, we could take that, once the FSP, fission surface reactor, is developed, that partnered with an electric propulsion system, something like maybe our AEPS. You put those kind of together. Those are each being kind of higher TRL. You put together to make a nuclear electric propulsion system. So I would guess, I'd probably pick, if I was guessing, I feel like NEP could happen maybe a little before NTP, but it's right on the cusp, and I think we really need both.
Okay.
So I'm going to stick with nuclear.
Okay. Dan?
So if you look at the money that's going into the space industry, the things that venture capitalists want to do and that young groups of kids want to put forward as VC ideas, almost all of them require way more delta V than we currently have. So sometimes by factors of 100 or 1,000, it's quite insane. Delta V has two parts to it. It has ISP, and we get ISP from nuclear power is one way, nuclear thermal, because then you can have just hydrogen. You don't have to have anything heavy. So you get your ISP that way. The other place is the mass part, and where does the propellant actually come from? So the other big development, and this is not exactly propulsion development, but the other development is in situ resources and being able to work with things already outside of Earth's gravity. I think to really realize all the things we'd like to do in space, we need both things. We need real nuclear power, and we need the ability to get propellant without carrying it from the ground.
Troy?
Yeah, so reliability is a big one, right? Kristen, you were talking about going to Mars. There's a, 8-ish minute communication gap potentially there. So how do we take these technologies that are being developed commercially by the government, by academia as well, and push those into a reliable sense where we can trust a human life sitting on top of that system and go into Mars, which is, it's several minutes of communication lag. So that ability to harness the technology and put it there in a controlled state, in a very reliable state, I think is going to be a big one. But opening up, possibilities is huge. This is, Dan and I both kind of live in this world of 15, 20 years ago even, universities were barely doing anything in space. And now we have the opportunity to launch things quite regularly, which is great. I think that's going to be another big thing. I'll talk about this a little bit later, but we put a payload on the moon that we literally ordered parts on Amazon for. So taking things out of a very cost prohibitive, technology prohibitive realm and putting them in the hands of university students or small businesses or whoever's coming up with the next great idea, I think that's going to be a huge step. NEP is a great step that's going to enable lots of distant and high-powered opportunities. And I go back to this idea of just relighting an engine. How many times can we do that? What about throttling and thrust vectoring? Those are still very huge and very complicated things, especially when you talk about maybe landing on the moon and then getting off the moon again, or Mars, wherever you want to go. So I think, but again, both of you hit the nail on the head here, but there's a lot of opportunity to press into some of these technologies as long as we can keep them reliable and safe and demonstrate their efficacy and ability to work, without human in the loop necessarily.
I think, can I
Go ahead.
jump in? I think, where you're going with that too is, I think we've seen a lot of advancements like with additive manufacturing and then the specialty metals, right? Because these are really harsh environments for that survivability, which then will lead to the reliability and the confidence that we'll have. So I think another area for continued investment in research is really kind of from the materials aspect of it. So what can we use? And then how can we do things cheaper? Can we, are the parts on Amazon good enough and going to be reliable enough versus kind of more of the exquisite things that we've seen? But we do know it's a really harsh environment, so I think there's a lot of opportunity to continue on that, like Troy was saying. And I think that'll help drive costs down too, which then gives us more access.
Yeah, you hit an interesting point. I had one of my mentors, former chief engineer and project manager for SSME back in the day, used to say every problem comes down to a materials problem. Just remember that. Some of you might remember Otto Getz, that name running around back in the day. Dan and Troy, let me go to you, because to make this kind of future happen, the students here at SciTech, 2,000 of them, as Clay says, plus everybody here in the audience, what do we need to do and how do we need to change our preparation of the students in terms of the courses, in terms of their preparation? What do you see that we need to do, and what is happening at Embry-Riddle and USC and other places to help facilitate that? And then Kristen, I'd like for you to maybe comment a little bit too on what you need from industry that would help frame up what needs to be done in academia. So Troy, why don't I start with you?
Yeah. So, we were joking in the green room a while ago. I'm going to tell you and Joe's story there about how Purdue walked into doing some EP work, right? It happened because there was only one place doing it at the time, right? So at Embry-Riddle, we actually have a rocket propulsion track within the aerospace engineering degree, but it's still prohibitive in how do you get students to do hands-on work with a rocket test fire, right? I mean, there's
Safely.
Right, safely, that's the word. So there are opportunities to do that at scale, right? I remember early on when I got to Embry-Riddle, they were pouring sugar and just to practice building a solid rocket at one point. So there's certain things like that where the scale is appropriate for students. Fundamentals-wise, engineering-wise, I think that's a whole nother discussion we can have on education of how do math and physics and engineering all play in together. Where are we in the state of all that as a country? But I think there's a lot of great universities doing a lot of great work on the academic side. having these partnerships with both other universities, with government, with industry is hugely important, because students who come back from an internship and that experience tend to have some pretty clever ideas. And a lot of those ideas end up, at least in my lab, I'll speak for myself here, you know, we have a little lunch table, and some of the best ideas came from 2 or 3 people sitting at the lunch table, and all of a sudden there's a SciTech conference paper, and then the next year there's a proposal, and then the next year there's, you know, something bigger. And you know, then we're putting a payload in orbit. So those kind of opportunities are great. The relationship between industry and academia is incredibly important, because if we can't put out students with a skill that you know you need, what are we doing? And I think that we all need to be very cognizant of that on both sides, for sure.
Dan?
We're kind of lucky at USC in Los Angeles because of where it is, and particularly as far as rocketry goes, because we're not fortunate enough, or most places aren't fortunate enough, like Purdue, to actually have rocket test facilities basically on campus or very close to it. But in Los Angeles, they say Southern California is a desert. Well, most of it is, and the Mojave is where a good part of rocket testing is done. And so our students can drive about 2 hours and be able to launch to a pretty good launch ceiling. And then to do space shots, they have to drive to either New Mexico or Black Rock Desert in Nevada. But there's a wide increase in the number of student programs that are doing rocketry. So maybe 10 years ago or something, when our students would go out to the Mojave test facilities, they would be almost the only ones there, maybe some high school teams. But now when they go out there, there's very often Berkeley, Michigan, there's not Purdue because they have their own places, but schools from all over coming, and it's really widespread. The other geographic advantage we have is that our students can do local internships at SpaceX, for example, and all the local aerospace primes. So one of the reasons that people come to our program is because of the undergraduate rocket lab that I mentioned, and the other is because we have a program that's space only. It's just astronautical engineering. Most programs are aero and astro, or you mentioned a rocket track within aerospace engineering. And places that are really well known for astronautics, Purdue, for example, CU Boulder is another, they're within aerospace engineering. But in high school, the students look and they say, oh, I want a space program, and they find us. So we're lucky that way. But in general, hands-on work is really where it's at. The students come, they take math and physics, they don't know what it's all for, but even as early as the freshman year, if there's hands-on stuff, they can go in and go shoulder to shoulder with upperclassmen. What's amazing is to watch large groups of students actually doing hands-on work, and they multitask in a way that people my age don't understand how to do. And at first I thought they were just wasting time, but then I watched how they actually work. They can actually be productive with their hands, monitor what they're doing on their phones, and have productive conversations with each other right there in the room. And all three things are, as far as I can tell, going along at a high level. So I used to be curmudgeonly about it, but now I'm saying more power to you. So current generations of kids have a pretty amazing career in front of them, I think.
Well, and I've seen it personally pay off at USC. In my AIAA days, had the opportunity to go visit your rocket team out at USC, and quite an impressive group. That was it was after COVID, and it was really great to see that energy and that enthusiasm at USC in particular that was really passionate about what you guys are doing. So saw it firsthand. So, Kristen, what do you need from the academic community to help have that skill base, that expertise you think you need to be successful.
Yeah. Well, first I want to thank you both and any other professors or academics in the room that are helping, because I think I've seen such a shift to, like you both were talking about being more applicable and hands-on. And I know when I was in engineering school, it was very theoretical and I didn't really understand how any of it was actually being used. And I've seen such a big shift, and I'm a grad from Penn, and I've been back there some and see it happening there and hearing you all. So I think that really helps make it more tangible and more real, and continues that inspiration and excitement. And then I think to what you were saying, when the kids go to an internship and then they come back and they've learned things, well, it goes both ways, right? So I think there's that kind of intergenerational learning that comes, and the breath of fresh air and new ideas that are coming in from students that haven't quite figured out, oh, maybe this can't work yet, but hey, it's out there. And so I think really want to keep the partnerships going, because we need the influx of talent, and then just continue to tell your students to, like, hey, don't think you have to hold back and be shy, because you'll be with folks who have worked in the industry or have the expertise from decades, but like their ideas are still really valuable. So I think we always do best when everyone gets their ideas out there, and then who knows what it can spark, right? This could spark that, and then the next thing you know, we have a new program or something that's being innovated and developed. So I just say thank you on that one. I think from a workforce overall in general, we don't need just obviously the engineers and the scientists are really important, but we also need to continue to think about like the non-technical, like the skilled workforce, because as we're going to continue to build, we really need to continue investing there. And college isn't for everyone, and being an engineer isn't for everyone, but skilled, especially from welders, technicians, it's really it's a craft and it's a skill that needs to be learned. So we need to continue to foster there too. So I know we're doing work on that. I know Space Florida's done a lot of work to help promote that workforce too, because we need that. We can have all these great ideas, but we need folks to help us actually build them and make them a reality too. So I think I kind of look at all of that. And then lastly, I'll just say, I think right now we're at such a historic time in space to be able to inspire the next generation, right? Like as we come up with the Artemis launch, like I bet if I asked most people in this room who wanted to be an astronaut at some point in their life, most of us would probably raise our hands, right? And maybe that was from watching Apollo moon landings, watching shuttles launch or return, or what that might be on the kind of eve of Artemis human spaceflight, crewed spaceflight now. I'm picturing in the next few weeks, hopefully the world is going to be glued to whatever device it might be, watching this launch and watching 4 astronauts go further the flight plans to go further than humans have ever gone before, but back to the lunar vicinity in the first time in over 50 years. And I think that is just going to inspire and ignite kind of that passion again for folks. And we need that it's on all of us to continue to foster that and let that kind of fire burn and grow into, whether it's specifically into a space career, but maybe into some other science or technology career. We want to continue to leverage that. So I think a great opportunity for us now.
Excellent, excellent. I remember some of the graduates came back on campus one day, and we asked them what did they not have that they thought they needed when they got to work. And one of them, as a former project manager, I broke out laughing. Well, you guys never taught us about budget and schedule.
True.
And it's like, okay, we're going to fix that one.
Yeah.
Got that answer.
It's also, there's a lot more teamwork. I've seen, the students today come back in and they know how to work on teams. They want to work on teams. I'm like, I think I had maybe one team project in my undergrad, right?
Right.
We just didn't really do that. And now it's a core part, and that's more realistic to what you see in the workplace. So I think students are coming out much more prepared.
Yeah, and it's so interdisciplinary, right? I mean, like you're just saying, we need people with the business skills. Yeah. We need people that can turn the screw. There are engineers that I wouldn't trust to do that, right?
Most of them I would not trust.
Most of them, fair. But we need people to do the design work. We need the technicians to build and test and operate, and all those are very different skills. So the teamwork aspect is certainly a very significant part of it also.
Okay, so there's one technology we haven't, well, let me back up, Dan kind of started a little bit of a thought process with me. You mentioned how the old papers are kind of getting put away and may not see the light of day, and we might forget that. how do we handle the future with artificial intelligence or machine learning and those kind of, how is that factoring into the classwork, the coursework, the teaching of the students? How's that factoring into what you're doing from a research and development perspective, or maybe even from a maintenance perspective? How is all that working? And I'd just like to get your thoughts for the audience of how you see that evolving, and where do you trust it, where do you not, how are you working it? And I realize I'm throwing a little bit of a curveball that we hadn't talked about, but you know, what the heck. I'm going to start with Dan, since he's the one that planted the seed that got me going.
Kind of a stretch from old papers in a file cabinet to AI running your business.
Hey, I'm making this up as we go here.
Well, I'll start by saying that like all professors, we're trying to figure out what to do about students who don't do homework anymore, but instead ask ChatGPT to do it. And actually, as far as that goes, 5 years ago, if you take a kind of a standard aerospace kind of, flow with friction or something, some kind of junior year technical problem, if you ask ChatGPT any kind of problem, it would give you a wrong answer, a misleading answer. Today, it gives you pretty much a correct answer. I haven't done this myself. I don't like AI. In fact, one of the reasons I like to go to JPL is that at JPL, AI means atomic interferometry. So it's kind of refreshing. But I have students and younger faculty members who of course, are very in tune to ChatGPT, and they tell me that the models, whereas aerospace was a few years ago a kind of a niche thing that the models didn't know, now they know it very well. So there is an area where I do like AI, though, which is in using small trained models to understand bodies of information that we know pretty well. In its traditional implementation as basically an interpreter and synthesizer of knowledge that we have already, AI is really good at that. The larger thing of asking a superintelligence to tell your business where to go, I don't know what to say about that. I'm sorry to say I am a little bit curmudgeonly about this. I'm one of these people who kind of don't see a good outcome for a lot of this. But so maybe I'm the wrong person to ask.
Yeah, so that is a good curveball, though. I'll admit that. So I think that there's a lot to AI. Dan, I like how you said that 5 years ago we'd get the wrong answer, but now using it as a synthesizer of information seems like a really good plan. We use AI in the lab for different things, but here's the problem that we run up against all the time is that it's still new enough to where training sets aren't available. So the data it needs to operate on and learn from, maybe we're making that up as we go and somehow biasing that toward a particular solution. So would I trust it to hand to Kristen and go, here, and develop your next rocket? No, just because that's a new problem, right? So are there things like physics-informed and other types of networks we can look at? Yeah, there's probably a dozen papers on that here this week. But looking at new problems, looking at using it as a tool to solve some of our problems, I think are two different things. In terms of the design, just like we tell our students, right? You still have to go back and check your answer. I'm not going to go fly on an airplane that's never been tested, right? Same thing with a rocket. You're not going to sell somebody a rocket that you've never turned on before. So I think there's something to it as a tool. I'm not convinced that it's going to take over all engineering jobs anytime soon. So again, that is a strong pathway forward. We've got a ways to go with it still.
think from more of the business side of it, we're really embracing AI in terms of how we manage our work, trying to get more efficient in some of the project management things, being able to identify where we're having trouble staying on cost or schedule, things like that. So I think that'll really optimistic that's going to reduce some of the chart making busy work that none of us really want to have to do. We'll automate a lot more of that and just more databases. So I think there's a lot of opportunity from that perspective. From a more on the kind of technical side of it, we're starting, I should say, we're not all the way there, but we have our own kind of internal proprietary database using our own internal information, so an LHX GPT. But it really all say all of our a lot of our analysis reports, and so when we're doing non-conformances and reviewing for what we've done before, we're now working on how do we leverage that body of information we've done before to help us more quickly identify what the problem, what this, maybe what the root cause could be, or how we go correct it. Have we already done this similar, repair before? Okay, let's leverage that and not start from scratch. So really trying to leverage the experience and work and body of work we've done. So that's where it is a little bit more of a controlled set of information that we can use that we know we presume was right before because we signed off on it before, and leveraging that to kind of pull into some of the design or repair corrections that we have. But I think also from a more broad perspective and how AI might be used, I think when I think from in space, it's getting more congested, right? I mean, the number of satellites in orbit is exponentially higher than it was several years ago and is on a path to continue to grow exponentially. And I think we're going to need to leverage more of the AI to help us kind of manage all of that, where kind of humans in the loop can't do that to the speed that it's going to be needed. Even other things we were talking about, humans in the loop in terms of communication. So where can we? I think there's an opportunity that we need to embrace AI that's going to help us be able to kind of more identify problems, be able to manage at scale where we can't really do that today as effectively. I don't think it takes humans completely out of the loop, but I think it becomes a real aid to help just identify things faster, especially in kind of the chaoticness of what's happening in orbit today.
Okay, a question from the audience that we really haven't touched on. One of the emerging technologies, rotating detonation engines. How do you guys see that might be playing into the future applications?
I'm going to defer to these two because
Okay,
got nothing.
maybe that was a bad question for me to ask. That's okay. We know that's out there, but that's fine.
I mean, I think that we need to continue. I know we're doing a lot of, we're investing in that. We're doing research.
Okay.
We're some of our R&D on that. I don't know enough about the technology to be able to speak clearly on it, unfortunately. But I think it's important to continue to evolve on that. So.
And I know it's,
I'm sure
it's
some of my friends
relatively
in the audience can
new,
help
so
answer that.
we'll turn that one over to
I have an expert in the audience if you want to ask, if you're going to come here after.
the technical experts.
Sorry.
Okay, so as we stand back, maybe to tie this back a little bit to Goddard himself, if Robert Goddard walked in here today, what would you want him to see, or how do you think he would react to what he saw or what he started 100 years ago to where we are today? What do you think the reaction would be, and what do you think some of the big surprises would be for him?
You're looking at me, so I guess I have to go.
I'm looking at all of you.
I would hope that he would be, happy and proud of that legacy, just because now we've got, I don't even know how many aerospace companies are around these days, or universities. I think there were 70 some odd universities with an aerospace engineering program in the U.S., but other departments, doing space work. I think the access to space for people would be hopefully a good surprise for him, right? Just seeing a conference of 6,000 plus people talking about space, talking about aerospace engineering. I hope that's what he would see, right? And the ability for us to go and use that for good, for learning, for science, for medicine, for further developing where we are as humanity.
I think that's really well said. I mean, I think hopefully just in awe and impressed on what his one launch really sparked for all of humanity, right? I mean, like Troy's saying, I mean, what we have been able to take from space and bring back to Earth, technology, medical research, you know, would you have thought we'd actually have people on the moon? I don't, you know, have gone to the moon. You know, hopefully he thinks that's amazing. Maybe he'd also wish we were going even faster than we're going to.
We all have that problem.
So yeah, you know, because we've had some good big leaps forward and just continuing those leaps. But, yeah.
Good.
Well, he'd be gratified to have a spaceflight center named after him, I think. And he was thrust into a sort of a battle with the New York Times that claimed that he must be deluded if he thought that rockets could work outside the atmosphere. But he seems to have won that argument, and I think he would feel pretty good about that.
Yep. Engineering wins over public media. I love it when the facts win the story. What other technologies, we've talked about nuclear, we've talked about other things. What are some of the other technologies that you see coming down the road that are going to be important for the future? That's a theme that runs through a lot of questions here, is still peeling the onion on those technologies of the future and what we think might be coming.
I'll jump in. I think maybe we go back to talking a little bit about the you know, in-space maneuverability and in-space propulsion. You know, we have a lot of good work we've done kind of on the monopropellant, bipropellant, chemical thrusters, and that have done some amazing things. But then also on the electric propulsion side, you know, I think we're going to want to continue to see that advancement and continuation with electric propulsion. And we just have tested and delivered a AEPS system, so the Advanced Electric Propulsion System, that'll be used on NASA's Gateway. That's a 12 kilowatt system, so the highest powered electric propulsion system built to date. And I think, you know, what that'll help us with as well, and different propulsion elements, because I think we're seeing a lot of then the kind of multi-use systems, the kind of multi-use leveraging both the hybrid of both chemical and electric propulsion, again, helping with that maneuverability. You know, we've come a long way. One of the things I forgot to mention, I was thinking about earlier, and actually Troy talking about some of the Mars landings, and we were talking earlier about kind of CLIPS landings and being able to land gently on another surface that isn't Earth. You know, I think about a lot of the propulsion that we've done for years. I think actually thinking about the Mars, the sky crane, you know, being able to very gently place a very heavy rover, both Curiosity and then Perseverance, during that 7 minutes of terror, right, when there's no communication and you don't know if it's going well or not. And the ability to do that, we've proven that. So how do we continue, you know, for whether it's a human landing system, you know, other things we're going to need to land on the moon, eventually on Mars, but then that just that more in-space propulsion, and even the deep space probes and where we want to go. I mean, it'd be great to get even further than we've gone. Can we use, I mean, this is maybe a little, let's say this is probably a little more out there, but thinking more like some kind of ion propulsion powered with some nuclear, like could we get to the closest star to our solar system, Proxima Centauri, right? It's 4.2 light years away. So standard chemical propulsion is going to take tens of thousands of years to get a probe there. You know, maybe at some point, maybe not in our lifetimes, maybe the next generation will be able to continue to advance that kind of technology and get there and see if those exoplanets have life on them, and you know, they might be habitable. And yeah, so that's more a little bit further out, aspirational, but continuing that advancement, kind of the in-space propulsion side.
Troy and Dan, as you guys look further out with that academic freedom, what do you see coming?
So I mean, this is an interesting problem, right? Because it's a little bit chicken and egg. So does the technology drive in-space propulsion and maneuverability, right, is one. Does that drive the concept, or does the concept drive the technology development? And it's both, right? Because some of our students will come up with a crazy idea, and they'll go to work for L3 one day, and Kristen will allow them to, you know, work up some crazy idea. That becomes the next great technology. But it's that give and take between those, but also the interplay of all of it, right? So what about they call them the propellantless things like solar sails, other crazy physics things that we don't fully understand yet, right? So there's all that, but the interplay, again, going back to the interdisciplinary, as we go to land on Mars or the moon, optical systems get dirty. So how do you do precision landing when you can't see? That's a great question. So the interplay of all of it, I think, is huge. But that enabling technology going alongside the concept development is kind of, I think, the path forward of not trying to push one over the other or saying one allows the other or drives the other, but having those run in parallel.
You remind me of a thing that I was told about the few minutes of terror as the Mars Science Laboratory came in, that there was kind of an argument about altitude between a couple of sensors, and if I remember right, the radar altimeter actually won, and which was good. It had good answers, and the thing came down perfectly. I think I'm interested in the idea of going to Proxima Centauri. Robert Forward, the science fiction author who died a few years ago, he had a dream job at Hughes Malibu. He basically had the job of sitting there and just dreaming up ideas. No one has a job as good as that. Anyway, he wrote of a concept of basically pushing a spacecraft all the way there with microwaves, and then reflecting to push one back to Earth, so you would actually get data back to Earth. But, more generally, laser propulsion is something that may find a role. In terms of things that are sort of within reach, but haven't really panned out yet, but show a lot of promise, I think MPD thrusters, and specifically, maybe, I'm not sure about this, the Vasimir program. Do you guys know about this? The Variable Specific Impulse, I forget the acronym. I first heard about it years ago when I was skeptical, and more recently, it's starting to look reasonable. It may actually go somewhere, and I think that'll be a useful thing for us if it pans out. For the further future, propellantless technologies, zero-point energy of the quantum field is maybe a direction we can go. There are demonstrations. They're not very efficient. The ones I've seen require like 7,500 watts to produce a few hundred millinewtons of thrust. So I would call that a pretty low efficiency. But where there's an effect, it can become more effective, more efficient. So the best way to overcome the delta V limitations is to have energy and not require propellant. And we don't have warp drive. I see no prospect of a warp drive, but of all the new weirdo physics, I think zero-point energy is maybe the one place that might come to something.
Okay, good. For the students in the audience, what kind of recommendations or thoughts do you have for them in terms of what they ought to be thinking of, what they ought to do, how they ought to approach their careers? Any words of advice from your own experience that you'd like to share with the younger professionals and the students?
I keep it simple, and I talk about, when I think about like my leadership and what I've learned, I keep it ABC. My ABC is about staying authentic to yourself is the A, being authentic and just really understanding what drives you, making sure you're in a place that values, what you can bring to the table, and not losing sight of, your core and who you are. The B is about being bold. So take the bold moves, whether it's a decision at work or a decision to take a leap into something you want to try, or trying something new, whatever that is. But not be afraid to be bold, and then C, just staying curious. I think having a curious mind and always wanting to learn, to keep growing yourself, learn about new things. I think you just grow a lot more when you're learning a lot, and I think it's a great way to, you learn from each other. I mean, I'm learning every day, right? I'm learning from this panel too, and having that love of learning and that love of being curious, I think will continue, especially as engineers. I think continuing that curiosity and never kind of losing that curiosity is always good. So I say, if you're just starting your career, hey, this is a great time to be in engineering. It's a great time to be part of space. The opportunities are endless, so don't be afraid to go after them. Don't be afraid to continue challenging yourself when you're getting stagnant, and yeah, and enjoy the ride. It's hard to predict what might come, and I could never have predicted my path. Most of us probably couldn't have, and yeah, and just enjoy it along the way.
Good, good. Dan?
One piece of advice would be don't chase grades. I think a high grade point average is useful if you want to go to grad school, because they're still kind of snobby about grades. But for industry, most of the people who want to hire you in industry, they didn't get that high GPA anyway, and they would tend to mistrust people with a 3.9 or a 4.0 as being people with a short-term memory and who prioritize study. So I think from an industry point of view, there's probably an optimal GPA, and it might be around anywhere from a 3.4 to a 3.6, maybe 3.3, somewhere in there, because it shows that you're good enough to know the material, but you didn't fixate on it. You did all kinds of other things. I think when you go out to companies, they want to see what you've done and what you can do. They don't care so much about classroom stuff. So this is why sorry, broken record time. The hands-on student groups are really a big deal, because if you do something in these extracurricular activities, then you'll have something to actually show. At USC, we have a couple things. We have the extracurriculars, but actually we have as part of the regular curriculum, we have a project lab where students actually build stuff. And I think most aerospace programs have project classes, and actually even there, you can develop something that you can show to recruiters, and that will take you really a long way. But outside of that, I would agree with what Kristen said. Stay open to new opportunities, and be prepared to talk to any random person that you meet, because you never know who's going to be the key to your future.
Good point. Very good point.
Yeah, and I think both of you hit that really well. Get involved. The more experience you have, the more you can tell a recruiter, man, I struggled with this thing, but we figured it out. That's a huge one. But be teachable, right? And in the pursuit of your crazy idea or your novel idea, learn from somebody who's done this for their entire career. But don't take that as the gospel, right? Take it and work with that and mold it into your own.
Right. Excellent. So I have one last question, and I already know Dan's answer because he jumped ahead a little bit on me, but that's okay. I'm a big Star Trek fan. So in 1996, in the Star Trek movie First Contact, Scotty informs everybody that Zephram Cochrane invented warp drive and had its first successful flight on April 5th, 2063. What do we need to do to make that happen? Troy, I'm going to start with you.
I was going to say L3 is going to build that. There, you got Kristen working on it already. That's. I started off my comments here saying that the fundamental physics have been known for 400 years. So, where's warp drive in Newton's work? We've got some further study to do, I think. But I think there are people, there are facilities. We're getting there. What'd you say, 2063?
2063.
Okay, so we've got a few more decades to get there, but maybe I'll be retired before that. So we'll see where that goes.
Dan, I think I already know your answer.
2063 is a pretty strict timeline based on what we know today, I have to say. So, I've been going to do AIAA meetings over the years, and there's always one or two sessions on advanced propulsion, or at futuristic concepts. They call it different things at different meetings. And there's pretty entertaining things that show up in these sessions. Interstellar ramjets with magnetic things that suck in plasma, and there's all kinds of interesting concepts. Warp drive specifically, I don't know the physics to make it happen. Wormholes, what you see on Star Trek, they're big enough for entire starships to go through, and you can fit a whole city inside. Real wormholes seem to be of atomic scale, and they rip apart till you get nothing but no information propagating through. So I'm not sure wormholes are going to be anything we can use either. So, so I don't know what's going to actually be warp drive propulsion by 2060s.
I mean, I think I'm with these guys. I'm not sure it's going to be by 2060s. I mean, as much as I would love to be beamed away and not have to get on an airplane and get there faster. But yeah, I think, like Dan's saying, I mean, there's a lot of advancements in the advanced propulsion. So I think we're going to continue to see more quickly, ability to go places faster, fast, but I don't know if we'll get to warp drive. But I do want to call it one of the things that's, I think, really valuable in Star Trek, not so much about the warp drive part, but that jumps out to me is that at first it is an inspiration for innovation, right? Some of the concepts some of the advanced computing and more instant communications things, that's more real life today that we never, that was sci-fi back then, right? So I think great for kind of that inspiration of innovation. But then also what jumps out to me is the ability to have the teams really working in kind of a multinational, multi-planetary, species kind of working together in the unity and collaboration. And we see that kind of multinational work today being, really important to a lot of our advancements. So whether it's ISS, I mean, the crew coming home here is, 2 Americans, a JAXA and a Roscosmonaut, and then the Artemis crew that's about to launch. We have a Canadian Space Agency astronaut of that, and over 60 some countries now as part of the Artemis Accord. So I think really we talked about teamwork a lot today, and I think that being able to come together with kind of a unification for kind of that good for humankind going forward as we explore space, I think is something we can take away from Star Trek as well, and we see it today.
Well, excellent. Well, let's please thank Kristen, Dan, and Troy for their great recognition of Goddard and his legacy. We really appreciate your time and effort and all of the insights. Thank you so much.